We will see the solution of set 4 questions. First question is, consider two semiconductors X and Y with intrinsic carrier concentration 4.8 into 10 to the power 8 per centimeter cube and 2.2 into 10 raised to the power 8 per centimeter cube respectively, with material constant A naught equal to 11 and 15 respectively at room temperature. What is the ratio of band gap energy at the given temperature? Ni is equal to A naught into temperature raised to the power 3 by 2 multiplied by exponential minus Eg divided by 2 kT. Now we will write the equations for intrinsic carrier concentration with respect to material constant A naught. Here NIx represents intrinsic carrier concentration of semiconductor X. A naught X is the material constant of semiconductor X. T is the temperature, which is 300 Kelvin, as it is already given that the semiconductors are present at room temperature. Egx represents the bandgap energy of semiconductor X. And also we will assume that kT will be approximately equal to 26 millielectron volt. Now we will write the same equation for semiconductor Y. After rearranging equation, you will get the value of bandgap energy of semiconductor X to be equal to similarly we will get the bandgap energy of semiconductor Y to be equal to 2 kT natural logarithm AOY multiplied by temperature raised to the power 3 by 2 divided by intrinsic carrier concentration of semiconductor Y. We are supposed to find the ratio of these two band gaps. The ratio of band gap energies of the two semiconductors come out to be around 1.137. Next question. Given that the bandgap energy of gallium arsenide is 1.42 electron volt at room temperature, the maximum photon wavelength for electron hole pair generation will be. You know that wavelength in micrometer of the electromagnetic wave required for conducting photoelectric effect is equal to 1.24 divided by band gap energy in electron volt. Band gap energy is provided 1.42. Therefore, lambda in micrometer will be equal to around 0.87323 micrometer, and in nanometer we have to simply multiply the wavelength in micrometer by 1000. So you will get 873.23 nanometer. This is the final answer. Third question is, determine the value of N naught and P naught for silicon at room temperature if the Fermi energy is 0.22 electron volt above the valence band energy level. So we have EC, we have EF, and we have EV. It is given that EF minus EV is equal to 0.22 electron volt. Okay. And we are provided with NC, NV and band gap energy. Band gap energy is 1.12 electron volt. And you also know that band gap energy is EC minus EV. Now EC minus EF plus EF minus EV, plus and minus sign will cancel each other. 1.12 electron volt. EC minus EF is equal to 1.12 electron volt minus EV minus EF, and from the above equation you can put the value 1.12 electron volt minus 0.22 electron volt, which gives EC minus EF to be equal to 0.9 electron volt. You know that hole concentration is given as effective density of states in the valence band Nv multiplied by exponential minus EF minus EV divided by kT. After calculation, the whole concentration comes out to be around 2.19 into 10 to the power 15 per centimeter cube. Similarly, for N naught, we have formula effective density of states in conduction band multiplied by exponential minus EC minus EF divided by kT. kT at room temperature is 26 milli electron volt, which can also be written as 0.026 electron volt. After calculation, the free electron concentration comes out to be around 2.59 into 10 to the power 3 per centimeter cube. Now we come to the fourth question. In a degenerate semiconductor, the Fermi energy level EF is positioned at the edge of the conduction band EC at temperature T. At this temperature, the probability of finding an electron in an state which is located at EC plus KT is. You know that the probability for finding an electron in a state located at any energy E is given by Fermi Dirac probability function, which is 1 upon 1 plus exponential E minus EF upon KT. At room temperature, KT is equal to 26 milli electron volt. Since it is a degenerate semiconductor, you cannot apply Boltzmann approximation. You have to keep that in mind. Now we put the value of E to be equal to EC plus KT. 1 divided by 1 plus exponential EC plus KT, and you also know that EF, which is Fermi energy level, is given at the edge of the conduction band EC. Therefore, EF is equal to EC. EC will cancel out. We have 1 divided by 1 plus exponential KT divided by KT. So, the required probability will be around 0.269, which is the final answer. Now we come to our last question, which says for an n-type semiconductor having doping concentration 5 into 10 raised to the power 15 per centimeter cube and intrinsic carrier concentration equal to 1.5 into 10 to the power 10 per centimeter cube, then shift in the Fermi level with respect to the intrinsic Fermi level will be. Since it is an n-type semiconductor, therefore the free electron concentration will be approximately equal to doping concentration. And by using this formula, we can find the shift in the Fermi level with respect to the intrinsic Fermi level. By putting the value of n equal to nd in the equation, we will have after calculations, we find the shift in Fermi level to be approximately equal to 0.33 electron volt.